All right, Lab 8 is due in lab today, but I guess you didn't start your calculations early enough and you want an extension? Is that it?
I'm going to leave the homework first.
Just to say yeah. Just say yeah. I didn't start it early enough and I want an extension.
I didn't start early enough. I'd like to extend it. I'll admit it.
All right. All right.
Even
Sure.
if we can do it by the end of the day.
Sure, yeah. I'm going to leave here at 4:30 today, and any lab that I have by 4:30 will be on time. The lab that we're doing today won't even take an hour. It'll probably take us what we're doing today during lab maybe 30 or 40 minutes at most. So that should give you an additional time as well. Just let me give you some additional help. I sent out an email yesterday that said that HGL, if you measure it, it's the pressure head divided by Z. But really what that is the measurement you took by the piezometer. And so I think a lot of people are struggling with calculating what does the graph of the EGL and the HGL look like. Well, first of all, the graph of the HGL is just what you saw for that one run where you took all of the taps. Now, what I'm expecting to see, the curve should look like, here was a point, then it was going down a little, and then maybe it went back up again. That's sort of the theoretical curve of the HGL. In reality, it'll probably more look like, since there are energy losses in there, it'll maybe look like that, possibly, for the HGL, hydraulic grade line. The EGL, energy grade line, is going to be the pressure head divided by gamma plus Z, so what you actually observed, plus the velocity head, V squared divided by 2G. We can calculate the velocity in the pipe because we know the diameter and the flow rate. So Q is the volume that you observed in some amount of time. That's how you get the flow rate, and it should have units of cubic meters per second. Area is going to be pi d squared divided by 4, and it's going to have units of square meters. And then the velocity through the pipe is Q divided by A. So V squared divided by 2G gives you, this is the velocity head term. So your actual measured piezometer elevation of the water plus the velocity head. Now when you graph the energy grade line, it should be above the hydraulic grade line because it's going to be the hydraulic grade line plus something, plus the velocity head. So if the HGL was based on a couple of points, you know, like it was based on maybe those points, then what you should expect to see is the EGL will be very slightly above those points at first because the velocity head was small, but then it's a lot higher. When the throat contracted, remember that the velocity is high through the throat of the venturi. Since the velocity is high, that means that this term is going to take on added significance. The pressure went down in the throat. Bernoullis equation says that when the velocity increases, the pressure will decrease. And so this divergence is sort of the essence of Bernoullis equation. When you see that the hydraulic grade line dipped down and then recovers, that's an expression of the Bernoullis equation. And the energy grade line, EGL, being above that is sort of telling you that the pressure went into the velocity head. That there is a little bit of a loss. There will be a downward trend because there is energy loss through that venturi meter, but there's not a lot. So the EGL line hopefully should be relatively flat. Yeah, it smells good.
What do you label the vertical axis?
It has units of length. And so you don't label it as length, you just label it as head. Right, head. Because this is pressure head, elevation head, and velocity head. Those are the three terms that are going into EGL. Yeah. Well, there's a figure in the handout that depicts that very thing. But that's awfully hypothetical. Your data should look like this. The k-value thing, that's maybe more up in the air. It looks like what it looks like. From the figure? Well, you'd assume that the figure value is correct and that your experimentally determined k-value is the thing that maybe isn't necessarily experimental. And then you find the difference between the two of those and divide by what you get, the k-value from the figure to find the percent error. Other questions from the lab? All right. So as a one-time gesture of goodwill, 4:30 is the due date for the submission deadline for the lab. All right. You're welcome. There's a homework assignment due on Thursday. This assignment on Thursday is dealing with Bernoullis equation. And Lab 9 that we're doing is experiment design. We'll talk more about that at the end of class today. But I just wanted to point out that it's Group B this week at 2 o'clock. And then Group A will be at 3. So, any questions before we get back into Bernoullis equation? Yes.
Do you do anything else with water gems this semester?
We are. We're going to have one more activity with water gems. And then next semester you'll do a lot with water gems. Yeah. You'll get your fill next semester for sure. Last time we talked about stagnation. And remember where we left off was the idea that if you put a tube down into the water, like let's say here's a river that's flowing, and you put some sort of a tube down into the water, that because of stagnation, because there's some streamline that has to stop at the opening of that tube. It won't stop at first. When you first put that tube down, then the water will go in a little bit, and that's what forces the water level up. It was initially the water goes in, but then it stops because the weight of this water is acting downward, and so the water's pushing down, and that's equal to the pressure that increases at the opening of a stagnation tube. If you take into account the added pressure over the area of the opening of that stagnation tube, that is what accounts for the added weight of the water that's elevated above the free surface of the water. So this is an example of stagnation. The Pitot tube is another. And in fact, the Pitot tube is a far more sophisticated way of measuring flow than just sticking a straw down into a moving river. Now, of course, the weakness of something like this is it works maybe for a liquid, but it wouldn't work for measuring the velocity of a gas. For the same reason that a piezometer can't be used to measure the pressure of a gas in a pipeline. But we found a way around that when we started talking about differential manometers. In the same way, now we have a Pitot tube that could be used to measure the velocity of flow with the principle of stagnation, but we can use it on a gas or on a liquid. And so a Pitot tube, let's take a tour around the Pitot tube and look at different aspects of it and talk about where it's connected into a pressure gauge. We're looking down on a Pitot tube from above. It can be oriented any way that you like, and I'll show you a picture of a Pitot tube on a plane in just a minute. But the velocity of the fluid is indicated, the direction is indicated by these streamline arrows. And think about this streamline that's going right towards the Pitot tube. Opening 1 is a static tap. the wind doesn't actually continue going through this tube. It actually stagnates at that, and there's a localized increase in pressure because all of the energy that was in the velocity of the moving fluid is transferred into a localized increase in pressure that's going through that tube. And if you follow the tube, if you follow the center of it, then you'll notice that here is a stagnation pressure tap. So we could take some sort of a pressure measuring device and find out what's the pressure of air inside of the pitot tube from that opening. And we assume that the pressure is the same everywhere inside of the pitot tube. But there's a second opening indicated with number 2, and that second opening, you'll notice, is sort of surrounding the central tube. This is hollow. So all around, there's a different air pressure than there is in the center of that cylinder that's going down through the stagnation pressure tap. And this is called a static pressure tap. And the opening is on the side. So think about the air that's moving past it isn't stagnating like it is at the opening. The air here is being trapped. It's sort of catching it, but when it's open at the side, the air is just going past it. It's not actually stopping the flow of the wind when it's oriented to the side like that. And so if we go back to energy grade line, you remember was the pressure head, elevation head, and then the opening one, the stagnation pressure tap. What's happening there is that there's a certain amount of energy in this air. If it's being used to measure the velocity of air, then some of the energy is in the velocity term, and all of the energy that exists as velocity at 1 gets transferred into an increase in pressure. So if you've got a certain amount of energy, then all of a sudden the velocity head goes away. That velocity has to go into the pressure. So there's more pressure at 1 than there is at 2. At 2, you're not really measuring the velocity at all because it's not causing the stagnation. Now, in the Bernoullis equation, if you rearrange Bernoullis equation, then you can come up with the pitot tube equation. And the pitot tube equation is derived from just saying that the velocity at 1 is canceled out, and instead of expressing the fluid in terms of gamma, you can keep track of the density of the fluid. And so you can find the velocity of the wind at 2 by measuring the difference in piezometric pressure at 1 and 2. Remember that P sub z is the pressure plus gamma z. And if you connect these two taps together here, the static pressure tap and the stagnation pressure tap, then that would be a differential pressure. So you don't measure each one of them absolutely, but you'd measure how much higher is the pressure in the stagnation pressure tap than in the static pressure tap. And so you'd have a differential measurement of the pressure. And if you're assuming that this pitot tube is on the same plane, that the z of 1 and the z of 2 is constant, and so if we're looking down on this from above, if it's on a horizontal plane and the z isn't changing, then we could just say that P sub z1 minus P sub z2 is the difference in the pressure between the two. And so you can find the velocity of the wind by just knowing what's the difference in pressure between point 1 and point 2. So that may seem a little bit theoretical, but let's put it into practice with this pitot tube example. This is showing an airplane that has a pitot tube sticking out of it, and that's how they measure the wind speed of the plane. I think that's probably a Cessna, that plane that's there, a Cessna 172. And so as it's flying through the air, it's the movement of the plane that is causing it to measure a certain wind speed. And they've connected a pressure gauge, one end of the pressure gauge to the static tap and one end of the pressure gauge to the stagnation tap. And the differential pressure gauge in this case has a range of between 0 to 1 psi. That's what the gauge, it maxes out at 1 psi. And so that's not a very big range, but it must have hopefully good sensitivity within that range. We're going to want to calculate what's the maximum airspeed that pitot tube can quantify using this gauge. And the way we're going to do it is by going through and applying both the Bernoulli equation and the pitot tube equation. Table A3 in the book gives us some properties of air at 60 degrees Fahrenheit. And according to that table, 60 degrees Fahrenheit air has a density of 0.00237 slugs per cubic foot. And these are traditional units, and you'll remember that a slug, there's 1.94 slugs. What's the conversion? 32.2 pounds of force is the same as 1.94 slugs. Oh, no, 1.94 slugs is the density of water per cubic foot. So the density of air is much less than the density of water. We can find gamma as the density times G, where we'd use 32.2 to get 0.0764 pounds of force per cubic foot. What's that? How did I get this?
No, like, what's the conversion for slug?
Oh, well, what I was saying earlier was that the density of water is 1.94 slugs per cubic foot. And what we know is that, let me jump to this slide from early in the semester because I think it lays out more clearly than I can on the fly here. Slugs versus, here we go. A slug is 32.2 pounds of mass. And a pound of force is when you've got a slug accelerated at 1 foot per second squared. And so these are really maybe the most salient conversions for slugs and pounds. Is one slug is 32.2 pounds of mass because G is 32.2 feet per second squared. And so that the main definition converting slugs and pounds is that if you accelerate one slug 1 foot per second squared, that is a pound of force. All right, so let me jump back to the example here. What we had is the density out of the back of the book defined in slugs, and we can from that get the unit weight of air in traditional units. .0764 pounds force per cubic feet. The maximum change of pressure that this gauge can measure is 1 psi. That is 1 pound force per inch squared. We can multiply that by 144 square inches per square feet, and we get that the change in pressure maximum that can be measured is 144 pounds of force per foot squared. Let's just say, for example, that was P1 was 144 pounds force per foot squared, and P2 is 0 pounds force per foot squared. Why do you suppose I chose, if this is just a difference, why did I select P1 as the greater of the two pressures rather than P2 being the greater of the two? because it's taking a direct blast of all that wind. Yeah. The pressure will be higher at 1 because it is causing stagnation. The wind is blasting into that opening, whereas opening 2 is sideways to the wind. And so the force of a streamline all of a sudden stopping, it doesn't have any of the extra pressure because it's not causing a streamline to stop. That's why I picked P1 to have the positive amount and P2 to be 0. Implicit in the definition of stagnation is that V1 is 0 because the wind stops at the opening of that tube. V2, we don't know. We're going to try and find out what is the maximum velocity that this can quantify using the pressure range that we can measure. And we're going to assume that Z1 and Z2 are equal. And I think you can see why that's the case. Is that this airplane is flying through the air, and even if it was going up, right here on the edge is the static tap opening. So here on the side, and then here's the front is the stagnation tap opening. They're not very far apart. Even if it was flying straight up, we wouldn't really have to keep track of the Z because the difference in elevation is going to be so negligible, especially in a gas like air. You know, even if we were using the pitot tube to measure the difference in pressure in a liquid, as close together as those two are, it's going to be negligible, the Z1 versus the Z2. But since it's flying horizontally in this example, that's why we can have Z1 and Z2 be equal. So we look at Bernoullis' equation, and here's the form of Bernoullis' equation where each term is in terms of pressure. You know, previously I've written Bernoullis' equation where each term in the equation is in units of length, and that was where we're saying pressure head, elevation head, velocity head. Here it's not in terms of length, but the units are going to be for each term units of pressure. We can cancel certain things out. We've got the P1 plus gamma Z1, and since Z1 is equal to Z2, we're going to cancel out the Z1, plus the density V1 squared divided by 2. We cancel out the Z2 term, plus the density V2 squared divided by 2. And we also canceled out the V1 term because the velocity was 0 at the opening of the pitot tube. Okay. So we can rearrange this. Well, we don't even have to rearrange. What it's saying is P1 is equal to P2 plus the density, the velocity 2 squared divided by 2. Or we can rearrange that, and its V2 is 2 minus, oh, not minus, P1 minus P2 divided by the density to the 1/2 power. And that's just exactly what we saw on the previous slide with the pitot tube equation. The pitot tube equation said that for some fluid density, and the density that you use is whatever the pitot tube is experiencing. If it's moving through air, then you'd use the density of air. If the pitot tube is in a pipeline that's filled with kerosene, then you'd use the density of kerosene. Now, strictly speaking, the pitot tube equation is the difference in the piezometric pressures, but here, since it's horizontally inclined, remember what we said is Z1 and Z2 are equal. So it just becomes the difference in the pressure. We can substitute in the numbers now. V2 is going to be 2 times the pressure difference, which was 144 pounds of force per square foot, divided by 0.00237 slugs per cubic foot to the 1/2 power. Okay. That is 348.6 feet per second. Remember that the definition of a pound force is it is a slug accelerated at foot per second squared. So the units do work out on this. If you substitute in pounds force for slug per foot, slug times foot per second squared, then all the feet units will cancel out except for one in the numerator, then we'll squared. Then we'll have seconds squared in the denominator. We'll take the square root of that, so the units do work out. 348.6 feet per second squared. We want in this problem to know what is the airspeed in miles per hour that will be measurable. And the way that we convert is, first of all, there are 5280 feet in a mile, and you multiply that by 3,600 seconds per hour. So the velocity, 237.7 miles per hour. That's probably faster than a Cessna can actually fly, but it's just an example. Sure, yeah. A pound of force, LBF, comes from, it's one slug being accelerated at 1 foot per second squared. So let's substitute that. 144 pounds of force, so it's 144 slug times foot divided by second squared. Okay, so these feet go up in the numerator, so it's feet to the 4th divided by feet squared. So that leaves us with feet squared in the numerator. These slugs cancel out and the seconds are in the denominator, so it is foot squared divided by second squared to the 1/2 power, and that's how we get up with the foot per second squared. Other questions? Evan, how does a pitot tube work? Okay. Okay, all right. Pretty good. Remember that it only goes in at first. Like on an ongoing steady state basis, the air actually isn't going into the pitot tube, but rather it's causing a pressurization of the pitot tube because it wants to go in, but it can't because conditions in there are static. You know, if we zoom in on that diagram, you know, the wind is going through and it wants to go in that little tube, but that little tube at the end of it is connected to a pressure gauge that isn't allowing air to flow through it. And so since the air wants to go in but can't, there's like a boosted pressure in that center part of the pitot tube. There isn't a boosted pressure in the casing around it. You can see that this static pressure tap is connected to the outside casing, and there isn't an increase in pressure because the streamlines just go right past it. The wind isn't being stopped by the opening as it is here in location 1. If you have a quiz at some point, you might be asked to be able to explain something. You know, conceptual questions are a really good way of weeding out students who understand the concepts with students who can plug numbers into equations. And what I really hope is that you're able to do both. Plug numbers into equations and also understand the concepts of what Bernoullis equation tells us about a pitot tube. Bernoullis equation, like why is this Bernoullis equation? How does this relate to the Venturi that you saw in the lab? Remember the Venturi in the lab and that diagram that I showed at the beginning of class of the divergence of the energy grade line and the hydraulic grade line is that the velocity head is what separated the two. The energy grade line is always above the hydraulic grade line by the amount equal to the velocity head. And here, how that ties into this kind of a device is that it's the velocity head that all of a sudden stops and is transferred into the increase in pressure that's measured in opening 1. That's at the heart of this first example. So let's say that we took a pitot tube and instead of measuring the wind speed with it, what if we wanted to try and measure the flow rate through a pipe? Here we have kerosene moving through a pipeline, a vertically oriented pipeline. So for some reason, we've got a pipe that's up and down, and kerosene is moving through that pipe. Maybe we're in a refinery or something. The specific gravity of kerosene is 0.81, and it's flowing downward through the pipe, and we have a manometer that is connecting the static tube and the stagnation tube. So we haven't really depicted how the openings at the end of the pitot tube were how the pressure difference was being measured. Here, the manometer is measuring the pressure difference. And we want to find out if the deflection here, y, is 18 centimeters, then what is the kerosene velocity in the pipe? Now, I'm going to give you some time to do that first part that's indicated in red there to begin with. Write the manometer equation between 1 and 2 through the pitot tube. Remember, the manometer equation is just the same thing as the hydrostatic equation. So you'll start off by saying P1, so you're starting at 1, and you're going through the tube. So let me draw the path for you. Let me trace the path, and then you write a hydrostatic equation. How do you get from P1? It's going to be plus this, minus that. Remember, whenever you go down through a fluid, it's plus gamma of that fluid times the elevation difference. Then whenever you go up through a fluid, it's minus gamma of that fluid times the elevation distance. So it's P1 plus blah, 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 minus blah, 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 so on and so forth is equal to P2. So go through that process, and the route that you should take is starting at the opening at 1, you're going down through the pitot tube, and it goes to this side. The pressure is greater here, and this is a reflection of what the pressure is at 1. And then you're going up now through it, and you're at 2. So here's the route again. Starting at 1, going down through the center of the pitot tube, connecting to the stagnation pressure tap, going down through the manometer, and this is kerosene, and now the blue stuff is mercury. So now we're going through mercury, so the hydrostatic equation is going to use the gamma of mercury through that part. Mercury, by the way, has a specific gravity. Sg of Hg is 13.56. We'll just use 13.6. So going up through the mercury, then we're going up through kerosene again, and exiting at 2. So try and write the manometer equation. It'll be a good way to harken back to the past. And then we'll solve that using the deflection of 18 centimeters. Starting at 1, we've got the pressure at 1, and then we're going down through kerosene, and so we'll use the unit weight of kerosene. There's kerosene inside of the pitot tube where there isn't mercury. It takes on the same fluid as it is measuring. And the distance is Z1 minus Z2. We don't know how far apart they are in numerical terms. We just know it's the difference between them. And then it goes down through kerosene still, the distance L, so it's plus gamma kerosene times L, and that puts us here at the interface of the kerosene and the mercury. Next, we just jump straight from this interface over to that side without any change, since we're moving sideways through a static fluid. The pressure doesn't change at all. So now we're here, and we're going to go up the distance y through the unit weight of mercury. So minus gamma of mercury times y, and then minus, now the distance is a little bit tricky. From this interface up to 2, the distance is L minus y. So that's what's indicated here. L minus y gets us the distance from the upper mercury interface to location 2, vertical distance, multiplied by gamma of kerosene, and then that is equal to the pressure at 2. So the next thing I'm going to do is group this by piezometric pressure. So group by P sub z is equal to P plus gamma z. And what I mean by group is we've got P1 plus gamma of kerosene times Z1 minus P2 plus gamma of kerosene times Z2 is equal to Y mercury minus kerosene. All right. And so what we could say is that this first term of P1 plus gamma of kerosene Z1 is P sub Z1. The second term here, P2 plus gamma of kerosene times Z2, that's P sub Z2. And it's equal to Y gamma Hg minus gamma kerosene. Any questions so far? Like, where did it come from?
Let's do the first one.
Okay.
Distributed to
Yeah.
the second one.
All right.
I don't see how it becomes P2.
What I did is I moved P2 over to this side, so that's where the minus P2 is. And then the gamma kerosene times Z2 comes from here. And so certain things are going to cancel out. Like, for example, the gamma of kerosene times L plus here, and then I've got the gamma of kerosene times L is minus there. So, for example, that's one term that's going to cancel out. But then I've got, for example, gamma of mercury times Y, and then here what's left over that didn't cancel out from the L's is the Y times the gamma of kerosene. So that's moved over to the right side term. So basically, if you just expand everything out and cancel out the common terms, then what you can do is you can group the things together by 1 and 2. So what I mean by grouping is just, yeah, you expand everything and cancel out the common terms, and that's what's left over. And the reason why we group it together is because what the manometer is measuring is the difference in piezometric pressure. So it's fortuitous that we're going to end up with a pitot tube measuring the velocity. The pitot tube equation says V2 is 2 divided by the density, and then it's the difference in piezometric pressures. Remember, we don't even know how far apart 1 and 2 are. We don't know what is the difference in the z's between them. But it turns out not to matter because the differential manometer automatically takes that into account, the difference in elevation between 1 and 2. It doesn't matter because the differential manometer measures the change in piezometric pressure. So if we combine this and the pitot tube equation together, combine the result of the manometer equation and the pitot tube equation, and we have to know what the unit weights are that we should be using. So for mercury, remember it's 13.6 that of water. $133,416 newtons per cubic meter. The unit weight of kerosene, $79.46 newtons per cubic meter. And the density of kerosene, that's easy to find because it's 0.81, and we know there's 1,000 kilograms per cubic meter for water, so it's 810 kilograms per cubic meter. Okay, so we'll substitute all of those values here into the equation that we've derived for the pitot tube here. So it's 2 divided by 810 kilograms per cubic meter, multiplied by 0.18 meters. That's the measured deflection at y. And then the difference in the unit weights. And all of that, take it to the 1/2 power. So we get V2 is 55.76 meters squared per second squared to the 1/2 power. And the reason that we're getting these units is you can remember a Newton is a kilogram meter per second squared, and that's going to cancel out the units of kilograms from the density. And what's left when we combine everything is units of meters squared per second squared. And so ultimately it's 7.47 meters per second is the velocity that's going through that pipe. In the problem statement, it says that, well, down here, the deflection is 18 centimeters between the two ends of the mercury manometer. So at a certain flow rate, you'd see a certain deflection. If the flow rate was 0, if there was no water going through there, then there wouldn't be any deflection because there wouldn't be any extra pressure on the upstream end of the pitot tube. But as the velocity goes up, the deflection does too. Well, so for that to be a meaningful question, if it was mercury in the pipe, then we couldn't have mercury as the manometer fluid. We'd have to have some different liquid. So maybe if there was mercury in the pipe, then we could use oil as the manometer fluid. And so, you know, if that was the case, what was the scenario that you posed? Oh, yeah, so you're asking what fluid do you know, how do you know what to use there? You always use it as what the pitot tube openings are in contact with. Yeah. So if it was water, then you'd use the density of water. Or if it was oil, you'd use the density of oil. It's whatever these openings are touching is which fluid you use for the density there. Questions? So Morgan, how could we use a pitot tube to quantify the flow rate? Now, we've just found out about the velocity, but what if we wanted to know Q through that pipe? How would we extend that concept? Exactly right. Cross-sectional area of the pipe, and knowing the velocity, then you can find the flow rate through the pipe. And it turns out it's very hard in an enclosed pipe to measure the flow rate. You know, we've been doing it in the lab by plugging up a hole and watching the well fill with water and holding a stopwatch. But that's not always convenient when you're in a refinery, for example, and you've got kerosene flowing through a gigantic pipe. There isn't somebody at the other end of that pipe with a stopwatch and a big tub that they're measuring the liquid accumulate in. And so there's a variety of different ways to measure the flow rate. Sometimes they'll use a really expensive and sophisticated magnetic ring that goes around the pipe, and they actually measure the mass flow rate of the fluid that's going past magnetically. Other cases they'll use a physical measurement like this to try and find out what's the velocity and then multiplying that by the cross-sectional area. A propeller spinning around? Yeah, sure. Like a paddle wheel? Yeah, they could. But remember, it would have moving parts, and the pitot tube doesn't. So anytime you've got a moving part, there's potential for breakage. All right, one of the homework problems you've got is problem 461. And piezometers are attached to some pipe, and they measure piezometric pressure. And so what you should keep in mind here for this problem is, first of all, Bernoullis equation can be expressed either in terms of head or in terms of pressure. And this is the version of the equation expressed in units of pressure for each of the terms. So here's pressure, here's the elevation above the datum times gamma, which will have units of pressure. And this is sometimes called the kinetic pressure. This velocity, what if it was in units of head, we call this the velocity head. Well, you don't call it maybe the velocity pressure. It's sometimes called the kinetic pressure, that term of the density times v squared divided by 2. So here you can group the terms in Bernoullis equation by piezometric pressure of 1 and 2, similar to what we've just done here. You're grouping the terms together. You know, what at location, if this is location 2, you're wanting to know the unknown velocity. And so you'll find out, well, what is the pressure at 2? You know, well, you don't know the absolute pressure at 2, but you know the difference in pressure between 1 and 2 because you've got these two piezometers. And these two piezometers tell you that the pressure at 2 is lower than the pressure at 1, right? That's what that deflection means. Since it's higher over here, that means that the pressure is higher. Now don't get confused saying, well, of course the pressure is higher at here because it's lower than it. You know, if this was a vertically oriented pipe, then yeah, the pressure is going to be lower here, but a piezometer measures the piezometric pressure, and so it's already taking into account the fact that it's lower. In other words, if there was no water going through there, those two lines would be equal. There wouldn't be that deflection, 6 inches. The 6-inch deflection exists because the velocity is going through the two pipes. And so the extra 6 inches is because of the velocity difference between location 1 and location 2. So you can tell that it's choked down to a throat here. Velocity 2 is going to be greater than 10 feet per second. And if you want to find out what is that velocity, you do the same kind of grouping procedure that was illustrated in this manometer example. You know, you basically write all of the terms at 1, all of the terms at 2, and start grouping in terms of the pressure at 1 plus the gamma Z1 minus the pressure at 2, the gamma Z2, and the delta H, what that's referring to is the difference in elevation between the two terms. All right, today in lab, let me give you the handout that we're using. Take a few minutes to read over the lab. I want to find something online to show you while you're doing that. It'll just take me but a moment. Let's talk about where all this is coming from. You may know that the degree that you're earning is accredited by a body known as ABET. That used to stand for the Accreditation Board of Engineering and Technology, but now it just stands for ABET. They decided that the acronym was well known enough that they didn't need it to stand for anything. Just like KFC no longer stands for Kentucky Fried Chicken, right? It just stands for KFC. ABET must have had the same marketing consultants. So anyways, the degree that you're earning is accredited, which means it meets a certain level of standards. And one of the things that ABET insists on is that engineering graduates have, as written in Outcome B, an ability to design and conduct experiments as well as to analyze and interpret data. So what we've been doing so far in the semester, experiments 1 through 8, we're conducting experiments. And you have been analyzing and interpreting data. But a much higher level function than conducting an experiment that you've been given the handout for is to design the experiment. Now think about what that means. It's not saying to design experiment equipment. It's not saying that you need to manufacture some device. But to design an experiment, what you're doing is you're thinking about what's the method and what's the procedure that should be followed in order to conduct an experiment. And in this lab, what you're going to be taking a look at is something known as the Hazen-William equation. We'll actually get to this equation's application later in the semester, but it's okay that you're going to be doing the lab experiment on it now because you don't yet need to fully understand all of its implications in application in order to observe it in the lab. This equation is meant to predict the velocity in the pipe when you have some measured pressure difference. And so how does that tie into this? So you need to design an experiment. And so in this assignment, what you're going to do in part 1 is create a lab handout similar to the lab handouts that I've been giving you each week. The lab handout should have a little bit of background information on the purpose of the equation that you're going to be investigating. And so you're going to have to do a little bit of research, maybe in your textbook or online. You can find a small summary about the Hazen-William equation. So you're going to give an introduction. You're going to present the equation and explain each of its terms. Now maybe the most challenging for you is you're going to have to come up with the procedure. Now, you've never used the equipment before, so how are you going to actually come up with the procedure to run a lab? Well, that's the exact same difficulty that you'll face in the field when you graduate and you need to start using equipment. You're going to start using it to conduct an experiment, and a lot of times that'll be an experiment that you've never run before. So you're going to be both familiarizing yourself with equipment and figuring out how to apply it in the same step. It's going to be back in the lab. We'll take a look at the equipment today. I'll give you an overview of how to measure the pressure, how to operate the equipment, but you're free to come back into the lab and observe it and take pictures and get the model number and measurements and revisit the lab as many times as you need as you're preparing this lab handout. And so it's going to include a step-by-step procedure. You're going to write what the procedure is, and you should include practical tips, little reminders of things to do. I'll mention a few things to look out for, but include them in the step-by-step to yourself. Ultimately, you are going to be the target user of this lab handout, but I'm going to review it and grade it separately. So lab number 9 is actually a two-part lab that will have double the value of an ordinary lab. You're going to get a full lab grade for the handout that you prepare, and then another full lab grade for conducting the experiment and preparing a report. The handout that you prepare should include a data table, and one of the things I try to do is include in the data tables only the things that you're supposed to record in the lab. I don't put every column that you'll be calculating in a spreadsheet, for example, because it gives the wrong impression in the lab of what actually is the data that needs to be gathered. And I'd suggest that you consider the same thing when you're preparing your own data table, that you figure out what measurements do you have to take in the lab and only include those measurements on the data table that you take with you. And, you know, spreadsheet calculations that you'll do later on is a completely separate issue. Include in your data table enough runs so that you'll gather accurate data. You know, sometimes, especially for example with the flow visualization experiment, it's a good thing that we took the measurement a couple of different times, because sometimes we were high, sometimes we were low, and if you get an average value over time, you might get closer to the actual value that you're trying to find out. In this experiment, what we're trying to find out is the C value in Hazen-Williams equation. It's basically a coefficient that relates how rough a pipe is. When you're using the Hazen-Williams equation, a rough pipe will have a really low C value, and a smooth pipe, a very smooth, nicely made pipe, would have a high C value. And so you're going to try and find out in the lab back here, what is the C value of this pipe? And compare it to published C values. Now, there isn't a C value in your book for stainless steel, but there are values published online that you should be able to find. So in a nutshell, that's it. It's a two-part assignment. One, you're going to create a lab handout, and you need to have that lab handout created a week from today. You'll be submitting it in MU Online. I've created an area in MU Online where you can upload it there. You won't email it to me. You won't submit a paper version of it. You'll just upload it to MU Online by next Tuesday at 2 p.m. And then you can actually conduct the experiment after you've completed the handout. And you're going to do it on your own time. And so what that means is that next Tuesday we won't meet for lab. You can just go do the lab by yourself in the lab area anytime you like. And that's something I want to emphasize, is that both the preparation of the handout and conducting the lab should be individual. You shouldn't have the same data as anybody else in the class. Everyone needs to conduct the experiment by themselves, individually. Somebody else can be there to keep you company, but you're going to run it once, and then they're going to run it a different time with their own data. Everyone should have unique data for that. So just to review the due dates, the handout is due a week from today, and then you can actually perform the experiment anytime between today and next Friday. So today, the 22nd, you may conduct it in between Tuesday the 29th. I put in you can start actually before the 29th. So here on the back of it where it says, you may conduct the experiment individually anytime that the lab is open between Tuesday, October 29th. What I meant to put is Tuesday, October 22nd. If you want to actually write the lab handout tonight, then you could go do the experiment tomorrow for anyone who wants to get done early. So you don't have to wait until next Tuesday to actually execute the experiment if you want. But the equipment will only be available through Friday the 1st of November, and then the report for the experiment is due on Tuesday the 5th of November.
We can do it at 9, or have to be here at 5.
Well, if you can get into the lab, I don't object to you being there, but I can only tell you that Patrick will be available to let you into the lab during ordinary business hours. Then nothing I can say will stop you. I trust you guys to treat the bench with care. Really, the risks involved with this experiment is, number one, that you'll tip over the pipe rack. And that's not far-fetched, because the pipe rack is really top-heavy. We'll talk about that when we're actually in the lab later today is it's a little bit unstable. So you're going to have to be careful not to tip it over. But I guess last week's one of the groups had a water spill, and you guys managed to turn the bench off quickly enough. And so I trust your ability to react to unforeseen circumstances. And I don't think that there should be any risk of that with this one. All of the fittings are nice and tight. So you can do it whenever you like. But we're not doing this just because I'm a mean guy. That's why we do a lot of things. But in this particular case, it's because ABET wants you to. It's not just because I'm a mean guy. All right? So I'll see you if we jump back to the timings here. Group B at 2 o'clock and Group A at 3 o'clock. We will meet directly back in the lab.